session 3, unit 4 of our financial modeling course. In this session, we are going to consider the distribution of the error term. By the end of this session, you should be able to explain the concept of normal distribution, test the residual for normality, and also find remedies for asymmetric distribution. Normality. The additional assumption of the classical linear regression or the linear regression model on the error term is to test for the normality of the error term. So we are testing as to whether the error term is normally distributed or it is skewed, or there is asymmetry in the distribution of the error term. Thus, we will need to show whether or not the mean of the error term is 0 and normally distributed. So one will ask as to whether or why we need to do such, because the error term is not assumed to be non-random or non-stochastic. It is known to be random. So why do we have to test for the normality of the error term? So given that there are reasons for everything, we have to understand that even though there are some critics who believe that financial data or models are they are oversimplistic, there is a likelihood that the error term will depart from normality. So departures from normality are typical of empirical economic and financial data. But how would that affect the normality of the error term? Perhaps because if there are asymmetries in the data set, this can be replicated in the error term, and also because the chance that this is replicated and also the possibility of there being being the existence of serial correlation or the presence of serial correlation is also high. So we are testing to see whether if the error term is indeed random. So we test the normality to see if it is indeed random, and that we cannot predict them given that the financial data are mostly considered to be autocorrelated or serial correlated. So it has been established that the last two, so after testing the normality, we have several means of testing for normality. So we can sometimes even use the high moment. The first two moments are the mean and the standard deviation, and they are not enough in testing for normality or in assuming normality. Sometimes we have to go further to check the higher moment, or the second moment, sorry, the third and fourth moment, which is the skewness and kurtosis. We have to consider them to see whether if the data set is indeed normal. So we have to understand that the last two moments must always supplement the task adequately. That is the task of testing whether the data set or the error term is indeed normal. So a normal distribution should not be skewed. That is, it should be found at the mean should be found at the center and should not be skewed, or the data should not be found at the extreme ends. And also we should have no fat tail. By no fat tail, we are simply saying that there should be a kurtosis of 3, that it should be mesochaetic. So the kurtosis should be equal to 3, indicating that there is no idea of excess kurtosis, and the kurtosis is actually 3. So which shows that the distribution is normally shaped, or it is bell shaped. So skewness and kurtosis are simply the third and fourth moment, and they are one way of testing for the normality of financial time series data. So test of normality. One will understand that in our earlier session we have considered the testing for normality, and we said that, or we are of the view that to test for normality simply means that we are testing for how the data set is being distributed. And in this case, if we are testing for the normality of the residuals, we are referring to the same distribution or normal distribution of the data set, or how the error term is normally distributed. Well, a popular test of normality is the Jack-Barra normality test, but we have other tests like the Shapiro-Wilk and the Kolmogorov-Smirnov, among other tests. But mostly for time series data, or for high frequency time series data, we use the Jack-Barra test because it has a capacity of handling data set with such high frequency. So the Barra and Jack formalize the idea of moment of distribution by testing the residuals for normality. So we're saying that this statistician or these persons were the first to develop this they were the ones who developed the Barra or the Jack-Barra test, and it was meant to test for the residuals, not unlike the other tests that only test for the normality in the data set. This were to test for the residual, that is the error term. So the Jagbera test is defined as we see in equation 3.4 and 3.41. So JB test is equal to T into bracket 2. So these are the B1, B2 are simply the beta coefficient, and the final result should be in a chi-square. The final answer should be in a chi-square. So equation 3.4 and 3.41 is simply an equation that is used in testing for the Jagbera test, and the B1 is explained as this and the B2 is explained as this. So this is B1, this is B2, and you can see that it's more of the third and fourth moment that we are considering, and we are considering the error term. So these are the error term and this is the standard deviation. So these are the equations that we use in testing for the Jagbera test, and these are the how the B1 and B2 are we arrive at the B1 and B2. So the Jagbera test has a chi-square distribution with a degree of freedom of 2, and it is tested under the null hypothesis that the data set or the error term is normally distributed. So assuming we have set a significance level of 5%, which is the usual significance level, and we find that we have reached a value of 0.00, which indicates that we have no proof, or we don't have enough proof, or we don't have enough value to affirm or confirm the normality of the data set, then we reject the null hypothesis. So under the Jagbera test simply has a null hypothesis of normally distributed errors. So if we are saying there is normal distributed errors, for us to be able to reject the null hypothesis, we should prove that the data set is not significant. So if the residuals are normally distributed, the histogram should be bell-shaped, and the JB statistics should not be significant. So what we are saying is that if the value is significant, then the residuals are normally distributed. If not, then they are not normally distributed. Okay, so here we are going to consider how we are going to test for the normality, or how we are going to create our residuals and use the values of the residuals to test for normality. So you could clearly see that earlier on we showed as to how we can create the residuals and also the square of the residuals and test for autocorrelation. So in the same vein, we can generate these same residuals and test for normality. So after we have been able to generate the residuals and save it in our eViews application, we can use it to plot this histogram. So for instance, in this histogram, one could affirm that this is the center, that is 0, and you clearly see that the mean or the average of the error term or the residuals does not rest on at the mean, which is the zero line or the 0 point. So you could clearly see that this data set is skewed. The data is not symmetry, or it's not equally distributed, as you could see that even there are fat tails, or the data are skewed, and also there are fat tails. So you could clearly see that this data is not normally distributed. So we can also use the eViews application, like in computing the original normality, where we go to the view, and under the view we choose the residual diagnostics and then we go to histogram, and with that we can choose the normality test in addition. So in as much as the application will present us with the histogram, it will also come along with the series of normality tests, especially with the Jagbera test, for instance, and also the skewness and the kurtosis of the error term. So for instance, in this our statistics, we have a mean of negatives, so this value is close to 0, and a median of -102 a maximum and minimum value, as we can clearly see. But here our focus is on the skewness and the kurtosis. So you could clearly see that the data is skewed, so skewed to the right. This is an indication that the data is skewed as most of the values or the distribution are found on the right side of the distribution. We said this is skewed to the right, so this is a skewness to the right, so the data is skewed. So we earlier said that for the data to be normal, it should have a skewness of 0 and a kurtosis value of 3. Here this shows that a skewness of 1.5 indicates that the data set is not normal, it is skewed, and also there is an excess kurtosis of 5.24, which is way above the 3.0 standard we have set. Also, a Jagbera value of statistics of 153.111 and a probability value of 0.00. We said that if we don't have enough proof to accept the null hypothesis, So we reject the null hypothesis that the data is normal because we should have a value of more than 0.05. Here we have 0.00, so indicate that we have to reject the null hypothesis that the data set or the error term is normal. So let's assume the issue of non-normality is a disease and we need to find remedy for it. We are saying that in most cases there is no known remedy for the issue of asymmetry, because after you have transformed your data, you hope that the transformed data will be normal. So if after all this transformation you still, or it happens that the data set is not normal, then there is nothing that you can do. But sometimes there are also some other models or other models that do not assume all those properties or do not require all those properties or the requirements of the ordinary least squares, like the quantile regression, for instance. Here the focus is that with quantile regression we are no longer modeling the conditional mean, and we don't expect the error term to be normal. So all the conditions of the ordinary least square do not apply with the use of quantile regression, because with quantile regression we are simply modeling the conditional median. That is a median which can handle, or which is robust to those extreme issues, like it can handle issues of extremity, or where there is skewness or ketosis within the dataset. So, but sometimes we can also consider some of the volatility modeling, like the Gash and Arch, among others. Some of the models that do not assume the normality, like the quantile regression and among others, also may be difficult to implement, and one can be less sure of their properties or as to how they can be used in making decisions or their generalizability. So for sample sizes that are sufficiently large, if you violate, or the violation of the normality assumption is virtually inconsequential. So we are saying that we have to appeal to the central limit theory, and that the test statistic will be asymptotically appropriate for our distribution, or it shows the absence of error of normality. So in economic or financial modeling, it is quite often the case that one or two extreme residuals cause a rejection of the normality assumption, because they will affect the JB statistic via ketosis. So if this is the case, one way to improve the chance of error of normality is to tidy up that data by effectively removing those observations. According to Brook 2008, so we find a way to remove datasets that find themselves at the extreme end of the data, or that will not, or the data that is not helping us in achieving our normality. Sometimes we can remove those data sets, and if we can identify those data. Other than that, we have to resort to the other forms of models or econometric tools or approach or methods that are used in modeling for regression, which does not require the strict rules of the ordinary least squares. We have come to the end of this session. That is session 3 of the unit 4 of our financial modeling course. In this session, we have explained the concept of normal distribution and tested the residuals for normality. And also we have considered a few remedies for the asymmetric distribution, that is when the error term is not normal. We have considered some of the remedies that we can resort to in modeling our data. Thank you. Thank you for your attention. As we come to the end of today's discussion, hope to meet you again in our next session.